Switches come with various types of interfaces. The most common ones you will see are Rj45 and transceivers. This is the Rj45 cable. Rj45 refers to the connector on the end of the cable, not the cable itself. The cable is known as a Cat cable. There are various Cat standards like Cat5 and Cat6. These are the cables that you will commonly use to connect devices like workstations, printers, some servers, and so on. We commonly see these types of connections running at 1 gigabit, but they can also run at 10 gigabit. This is a transceiver port. It's different as we can add a transceiver to the switch to control what that port does. Basically, a transceiver is a hardware module that we buy and insert into the switch. This means that we can use different transceivers to achieve different goals. For example, we may have a transceiver to connect two switches using fiber optic cable at 10 gig. Or we may use another transceiver to connect our servers to our switches using copper cabling. Or we may have a different transceiver again to connect two different buildings together using long-range fiber at 1 gigabit. The advantage is that we can mix and match the types of interfaces we use in a single switch. These transceivers use standards like SFP, SFP+, and QSFP. An SFP transceiver supports 1 gig, while an SFP Plus supports 10 gig and sometimes 25 gig. QSFP, or Quad SFP, is a larger connector, which is used for higher speed applications. It's really just 4 SFP Plus transceivers joined together, so it can handle speeds from 40 to 400 gig. But even though they're different physically, they operate in much the same way. For example, we can configure both of these port types with VLANs, IP addresses, and things like these. This is why we see a separation between the layers of the OSI model. The details at layer 1 can be different, while layers 2 and 3 can be the same. One physical difference worth noting is that the Rj45 Cat type of cabling supports different interface speeds, for example, 100 meg, 1 gig, 10 gig, and others. When two devices are connected, they will negotiate the best speed that they can both run at. This means that one device may need to slow down to support the other device. This is a feature called auto negotiation, and it's on by default. It's particularly useful on a switch where a variety of different devices connect. We can override this and set the speed manually if we want to. To do this, we first enter interface configuration. Let's add a description while we're here just to show how it's done. Then we disable auto negotiation with the No Negotiation Auto command. The speed is set with the Speed command. If we use a question mark, we can see the different speeds that this interface supports. For our example, let's set this one to 100 megabit. Transceivers are a bit different. They are physical modules that are installed into the switch port and are hard-coded to a certain speed. I learned this the hard way years ago, when I had a 10 gig switch and a 1 gig ASA firewall. I used a copper DAC cable to connect them. The DAC cable, as shown here, is a copper cable with a transceiver built into each end. Sometimes they're known as twinax cables. Anyway, the problem is that the transceivers on both ends were hard-coded for 10 gig, but the firewalls would only support 1 gig. I thought I could use the speed command to change the switch end to 1 gig to match the firewall, but it just doesn't work that way. Transceivers have a fixed speed that we can't change. When two devices are connected to each other, they can operate in full duplex or half duplex mode. In full duplex mode, the interface can send and receive at the same time. In half duplex mode, it can only send or receive at any given time. As you can imagine, full duplex is far more efficient. These days, full duplex is used in most cases. In fact, for interfaces to operate at 10 gig or faster, full duplex is mandatory. On interfaces 1 gig or slower, we can change the duplex mode. I don't often do this, but sometimes you'll be asked to try it for troubleshooting. Let's try changing a few interfaces to half duplex mode. We can configure a range of interfaces using the range keyword. This can save us a bit of time. Just as before, we need to start by disabling auto negotiation. You can probably guess that under normal circumstances, two devices will work out if they want to use full or half duplex, just like they did when negotiating speed. Using the duplex command, we can see the different options that we have. Not many really, so let's just set these interfaces to half duplex. Even though we will use full duplex wherever we can, you will find that in many cases, service providers will still use half duplex in some cases. When a service provider deploys a fiber service to your premises, which could be for internet, voice, WAN, or something else, they can use either 1 or 2 cores of fiber as shown here. If there are 2 cores, one will be used for sending data, while the other is used for receiving data. That makes it full duplex. On the other hand, they may only give you 1 core of fiber. In this case, it's half duplex, as it can send or receive, but not both at the same time. I'm not 100% certain why they do this. I think it's because it's so expensive to run new fiber in conduits underground. When they're running new fiber, they'll usually run a lot more than they need so they can connect more customers later. So if they run, let's say, 144 cores of fiber along the street, they can support 144 customers at half duplex, or only 72 at full duplex. In the end though, they're still able to get the speeds that they promised to you over a single core. What if auto negotiation were to fail? In this case, there are a few rules that interfaces need to follow. First, they'll use the slowest supported speed, which is usually 10 meg. Rule number 2 is if the speed is 10 or 100 meg, it will set half duplex. And rule number 3, for other speeds, use full duplex. Cisco switches have the ability to sense the speed of other switches, so if auto negotiation fails, they will try to set the speed accordingly. But if that fails, they'll fall back on the rules we've just discussed. Where we can run into trouble is if one side is full duplex and the other is half duplex. This is known as duplex mismatch. This could happen due to a fault or due to a configuration error on our part. When operating in half duplex, the rules are the same as when connected to an old hub. It needs to use carrier sense multiple access collision detection to detect collisions. Full duplex, on the other hand, doesn't need to use that. So therefore, if one side's in full duplex and the other side's in half duplex, one side will use CSMA and the other won't. The half duplex side will think there are collisions when there aren't, and it will run the back off algorithm, it'll resend frames and so on. The ultimate result is that the link will kind of work, but it will have degraded performance. Here are 2 questions for you to consider. Pause the video now if you can and have a think about them, or come back later and give them a try some other time.